So how does the particle behavior come in? The answer is that the quantum wave function does not describe something like an electromagnetic wave, which one thinks of as a physical thing existing at a point in space and fluctuating in time. The quantum wave function describes a probability wave. A probability wave. Quantum theory asserts that the wave function is all one can know about the system. One cannot predict with certainty exactly where the particle will be at a given time, just the probability. Isn't that so interesting though? Isn't that so very, very interesting? It is just the probability. And the shock at that point was that people were not used to that. People were used to getting deterministic answers. If there was an equation written down for something, like the moon, for example, which is a classical object, or say you or me or trees or cats or cars, people expected a deterministic answer. People did not expect, oh, you'll just give me the probability of something happening as an answer. That is not acceptable. People were not very happy about that, okay? The classical physicists. So you can start to see how there was this divide between the classical physicists and the quantum physics, okay, or the quantum physicists. An important aspect of this wave particle duality is the uncertainty principle. This has many repercussions for physics, but the simplest one involves the position of a particle and its speed. Heisenberg's uncertainty principle states that one cannot know the position and speed of a particle independently of one another. Here we go. So not only did people, quantum physicists and classical physicists, have to digest the fact that quantum mechanics was probabilistic, but here was a quantification or a quantization of the uncertainty and the uncertain nature of quantum mechanics in this uncertainty principle formulation or formalization, okay? So there is a even a quantification of what this uncertainty is in the form of the uncertainty principle. So this basically says that the better you know the position, the worse you will know the speed of a particle, and vice versa. So if you know the position, you cannot know the speed. Certainly you'll have some limit, some uncertainty limit on the speed. And if you know the speed, you cannot know the position with certainty. You will have some uncertainty on the position. And together, it's postulated in the uncertainty principle. So if you know its speed precisely, then the particle could be located anywhere. This principle is quantitative. I mean, is it really anywhere with equal probability? No. Again, there's a probability associated with finding that particle at a certain position. So it's not like you knew the position was here, last you checked, and it's going to be somewhere totally different, like on the other side of the universe or anything. No,